Welcome to Hot Chips 25. Keynote 2, Google Glass.
We're going to hear a different keynote in a equally, if not more exciting, new form factor, Google Glass. And our speaker today is Babak Parviz. He is the creator of Google Glass, and he's a director at Google X. Babak received his BA in literature from the University of Washington, a BS in electronics from Sharif University of Technology, a master's in physics, a master's in electrical engineering, and a PhD in electrical engineering from the University of Michigan. He completed his postdoctoral training in chemistry and chemical biology at Harvard University. Babak's work has been selected twice, in 2008 and 2012, as the invention of the year by Time, and has been put on display at the London Museum of Science. Babak has also held academic positions in the US and Europe, and has been involved in a number of companies ranging from startups to Fortune 100. So with that, I'd like to introduce Babak to the stage. Please come and tell us about your latest exciting toy.
Good afternoon. Thank you very much, Remy, for the kind introduction. It's certainly a privilege and an honor to be in your presence and talking about Google Glass. This is a very distinguished audience. I hope to tell you a bit about the story of Glass and what we've been up to at Google in the past few months and few years. It's a very short presentation. It will take probably 15 to 20 minutes. And then perhaps we can have a few minutes of questions and answers. And the presentation is really about three histories I'm going to tell you. And these three very brief histories are ahistorical and entirely inaccurate, but bear with me and we'll go through this. Hopefully it will set the context for Google Glass properly. The first one I wanted to tell you about is the history of computing in the past few decades. And you are intimately aware of this because you enabled that. So a lot of the brain power that enabled the progress of computing in the past few decades is actually sitting in this room right now. But if I go back to the 50s, if I go back to the 60s, predominantly computers were huge operations. They occupied big rooms, sometimes stadium-sized facilities. And if you wanted to use a computer, you had to get into your car, drive to the computer, and use it. And they really actually started the revolution back then. Now, in the 70s and the 80s, late 70s, early 80s, this picture really dramatically changed. So there was a switch to personal computing. The computers got a lot smaller. They started to appear in your living room. So they became much, much closer to the person. In a sense, they became a bit weaker, actually, compared to the big ones that I just showed you. But the paradigm shifted. So now the computer is in your house. It's something that's very personal. And you own the machine, and you own a lot of the data that is used. Another big paradigm shift was when these computers started to move around. So when the laptops started to appear, mostly in the 90s, and they're in heavy use today, and they've made a lot of progress, obviously, over the past few years. So that was also a big shift. Now that the computer is not anchored to a certain physical location, it can move around with you. For me, back in the 90s, when I got my first laptop, that was a huge shift from having to go to a computer lab and use a computer, or having to go home and use a computer. And then came the phones. And with the phones, not just connectivity of voice for the users, but data. And this really has been the leading edge, the story of computing and communication in this century. In the past 10, 15 years, these devices have been sort of the driving forces of a lot of consumer electronics, a lot of new innovations in computing and communication. Now, I would like to invite you to think about the few devices that we just saw in a row. the span is many decades. But you notice that the devices have become smaller and smaller. They have become more personal, actually. Once they were in stadium-sized facilities, then they show them in the living room, then they start to live in your briefcase, and now they live in my pocket, actually. So they've become actually closer to the user. They've become much smaller. And as they become closer to the user and more mobile, they've become faster to access. So instead of me having to drive to a computing facility, now this is how much time it takes for me to use a pretty powerful computer is in my pocket right now. So the question was, looking at this progression of platforms over many years, what is going to come next? What is the big potential platform shift that's going to happen after the smartphone? What is it that's going to be even more personal, even more mobile, and even faster to access? Is there an answer to that? And that's actually one of the driving forces behind what we worked on Glass when we started the program. And that was one of the things that we hypothesized, that this form factor actually might be the next one, because of a variety of reasons that we're gonna discuss shortly. So this is where we are with Google Glass today. A few thousand of these devices have been produced and released to the wild, so a few people actually in the world are wearing them and testing them right now. So let me actually tell you what's in the current form of the system. What is it that I'm wearing on my head right now? So what I'm wearing today is a standalone system which has a display. So as I speak to you, actually, I can see visual information. It's not a very large display. It's a display that's basically, the feeling is similar to a cell phone that you observe at arm's length. But it's entirely usable. It's NHD, so it's fairly high resolution for the size that it has. So it can show the user visual information. It also has a very nice camera, so it can capture visual information from the environment. So it can take pictures, it can collect videos. And we'll come back to this in a few minutes, because I think that's a pretty important aspect of the device. It has full audio, so it has multiple microphones. It can collect sound information from the environment, and also has a bone conduction speaker. So as I talk to you, I can also hear things, actually, that the device would like to communicate to me, even though you may not be able to hear it, because it doesn't have a speaker, per se. It has a bone conduction system in it. And these are all intentional, and we'll talk about, actually, why we've gone through these routes. It has a fairly reasonably powerful processor. It's a dual-core processor that can clock more than a gigahertz, and we have many gigs of memory in the system. For interaction with the device, we have a touchpad, a two-dimensional touchpad on the side, so I can touch this touchpad and navigate menus or control the device if I wanted to. And it also has a series of other transducers, and they're also pretty important. So it has 3-axis gyroscopes and 3-axis accelerometers as magnetometers. It also has a collection of radios. So it has Bluetooth capability, it has Wi-Fi, and many of these systems, not guaranteeing actually the commercial ones that will be open for purchase for consumers will have that, but also has GPS. So this device can talk to radios that are here, or radios that are radio signals that are coming from multiple satellites in the sky, actually, right now. So we have all this tech actually integrated into a standalone system that I'm wearing today, and it works. And just to give you guys a little bit of false history of our group, this is actually how much gear it took when we started to integrate all this stuff together to have the system. Because when we started, there was no such system. We wanted to have mobile people that could have all these capabilities. And it took actually some effort to start from there. This is a good friend of mine, Thad Starner, to start from what you see on this picture to what's on my head right now, which is comparable in weight to a typical sunglass. There's a number of aspects that are unique to this particular form factor. This is fundamentally different from a cell phone that lives in my pocket, a notebook that lives in my briefcase, or a computer that lives on a desk at my workplace or in my living room. A very important aspect of this form factor is extremely fast access to computing. So as I talk to you, basically, this is how long it takes for me to access a computer. So you see how fast it is, and we'll come back to this and see why this is important. The second important aspect that this has is that this has a camera that sees the world through my eyes. And that's unique to this form factor. We don't have other electronic devices that can live with me as I live my life throughout the day without any intrusions to my life and see the world through my eyes. So this device actually can do this. And this device is intimately also aware of not just what I see, but my gait, my pose, a lot of other things. So this device, for example, right now knows that I turn my head turn left. But we don't have other electronic devices that can do that. So that's also important as we start to interact with this new type of computing. The interaction mode of a person with a computer that lives on your head like this is fundamentally different from computers that we've had before. We're very used to keyboards, we're very used to mouse operation. Those are suitable for other types of computing, but not necessarily with a computer that lives on your head like this. Another unique aspect of this particular form factor is that this can potentially overlay an layer of digital information over what you see. So a lot of you are familiar with augmented reality. Even though augmented reality has not been the driver or the focus of Google Glass at Google, but it's a very exciting field, and I'm sure eventually it will come, and it has immense potential. So when it arrives, I think it can be a transformative technology. And in order to enable that, we need devices that can show you something digitally produced and superimpose that onto what you would normally see. And this form factor is needed, actually, for doing that. And the last point I wanted to make about the uniqueness of this form factor is about the display size. So a lot of you carry smartphones, and you've noticed a trend in smartphones that the displays have become significantly better over the past few years in smartphones. Not only the pixel count and the color gamut of these displays have gotten better and better, but they've also gotten bigger and bigger. So definitely people would like to have mobile devices with bigger screens because they're more pleasant to use. You can do more with them. But how far can you go? How much bigger can a cell phone get? Some people put tablets in their pockets, but how far can you go? There's just a limit of physically how big you can make these displays. So if you wanted to have a mobile system that would give you immense displays, maybe immersive, you need a different type of form factor. And the type of mobile devices that would resemble what I'm wearing today, that can put a display very near your eye, have that potential to be very mobile, very non-intrusive, very small, but at the same time produce images that are very sizable. And that's unique to this form factor. So it makes sense, actually, to pursue this form factor as a next potential computing and communication platform. Now, so we said, actually, it might make sense to look at the progression of computing over the past few years and land with this form factor. There's certain things unique about it. We've built something like this. We've integrated a lot of tech into this device. It works. But at the end of the day, who cares? Why would you want to do that? Who cares about the next computing platform? I mean, obviously, there's financial reasons to pursue, but whose life is going to get better, actually, if we make something like this? We've had two main reasons for pursuing this, and this takes me to my next two brief, very inaccurate ahistorical histories. The first one actually relates to how people have communicated with each other over the ages. So if I go back a few thousand years and see how people channel their emotions, how they communicated with each other, basically what we did was to talk to each other. So we had to be at the physical proximity of each other, carry our emotions through speech, and communicate. That was the only thing that we could do. With the advent of writing, actually, the extent through which we could communicate significantly expanded. So now you could write down what you thought and put it in some sort of mail and send it maybe thousands of or hundreds of miles away. Great, so the range has been extended. And when electronic communication arrived, first with telegraph and then other types of electronic communication, not only we had the long range of communication, but it got a lot faster. So you could channel your thoughts to brief pieces of segment of writing, and then they will go through wires and we would get the telegraph to someone else. So extended range, and now speed came. And with telephone, actually, we extended this from pure writing, actually, to voice. So now we can communicate over extended ranges very quickly, not with just text, but with voice. And email, in a sense, has been or other types of electronic communications that we have today, there have been extensions of this. So they're mostly text-based, they're very fast, and they can operate over very, very extended ranges. So basically, we cover the entire planet right now. And what we have today, basically, with smartphones is all the previous ones, plus untethering the communication point. So basically, now I don't have to be at the particular physical location to receive mail, paper mail, for example. I don't have to be tethered to a particular physical location to receive a phone call when we had the landline. It's completely untethered. So you can have voice, you can have speech and text-based communication readily actually communicated to you. What we haven't really had actually to this date, genuinely, has been a device, a technology that has been engineered from the get-go for visual communication from person to person. And that's one of the main drivers of Google Glass. It's true that you can take a picture, you can email it to your friend, but that is sort of an extension of taking a picture and putting it in paper mail and sending it to someone else. That's not really technology from the get-go engineered for pictorial communication. So we believe actually that this form factor may enable genuine pictorial communication. I have a device that sees the world through my eyes. It allows me to capture it very quickly. So all I need to do is either voice communication or with touch. I just took a picture of you. I can do 2 taps and share it with someone. It's that fast, actually. I will do that live if you like. So that's all it takes. And our group basically will see that. Or I can basically live stream what I see right now on the stage to our group at Google. So all this stuff is actually doable right now today, which is a fundamentally different experience from emailing our group and saying that I'm giving a speech on Google Glass right now. It's a fundamentally different experience of calling someone and telling them that I'm giving a speech on Google Glass. They can actually experience my life at this very moment with me and see through my eyes. So this device enables this, and I think that's important, actually. If we engineer this properly, we've taken some really interesting first steps, actually, towards it, but if we engineer this properly, I think this could be a very powerful communication tool between people. We've had cinema, TV, those kind of things that are mass media from one point to many for a long time, but point to point, we really have not had that many devices that have been engineered from the get-go for pictorial communication between citizens. And the third history that I wanted to talk to you about, this is the other motivator of Google Glass is a very inaccurate and a historical view of traditionally how we've looked for information. So imagine yourself a few thousand years ago, you have a question of what is the tallest tree in the world, or where's Timbuktu? How would you actually find that? Actually, it turns out a few thousand years ago, basically, you were out of luck. There was no way to figure this out. So error, crash, system crash. Over time, maybe a couple of thousand years ago, if you happen to be living in ancient Greece or some other advanced place, if you had a question, you would walk to a polymath or someone who knew a lot, and you ask your question, and hopefully they give you some reasonable answer. So at least there was some way to get some sort of answer. Not sure actually how reliable that was, or how accurate it was, or correct it was. It took also quite a bit of effort to do this. If you're not living in some center of population, again, you're out of luck. This really changed actually big time for 500 years ago with the advent of publishing, basically. Libraries appeared, so now this has been for the longest time actually our mode of operation. If I have a question about something, I consult a book. I somehow go to a library, look for the proper book, look through the book, and hopefully I find the answer. Yeah, and also this mode has changed very much so in the past 15, 20 years by digitizing a lot of information and making this information searchable by Google, Bing, other players that have offered this capability of looking for information. So now this is actually how long it takes for me to answer a question. Just about any question. If I want to know what's the capital of Nigeria, basically I take my phone out, unlock it, basically, and then go to a search engine, say my question or type my question, and I'll get some number of links back. I'll probably click on one of them. So within a minute or so, actually, I will get the answer to my question, which is phenomenally good, actually, considering where we came from. This is amazing. This is doable. So a lot of infrastructure actually goes into enabling this. But it still takes a minute. So from not being able to answer a question to taking months, to taking days, to taking minutes, we want to make it even faster, much, much faster. Someday, we're not there actually yet, and I don't know how long it would take actually to get there, but someday we want to be at the point that as soon as you have a question, you can ask it and you see the answer right away. Extremely fast. And I think if we ever get there, this would fundamentally change the meaning of knowing things. And that's very profound, actually. The impact of this is going to be incredibly large. We'll see, actually, where we get at what point in time, but we've taken steps towards enabling something like this. So even in this very rudimentary form of this device, I can communicate with it, I can ask it questions, and it does actually give me some reasonable answer back. It doesn't take that much time, within a few seconds. I want to make it even much faster. So this is a device that lives with me day in, day out. I wear it all the time. And it really actually significantly expands my knowledge base. That's one of the major drivers of Google Glass. So two main drivers for why we wanted to make Google Glass. One was to have a pictorial communication device. And secondly, to make access to various types of information much faster. These types of information range from what's the weather in San Francisco, to solve this integral for me, to what's the birthday of Napoleon, to what is it that I'm looking at. So this could be a variety of complexities, but that's where we're going. Now, so what does this device do today? After the presentation, I'll try to wrap up in a few minutes. I'll be around, so if you like, we can talk about it. It's very difficult, actually, to demo this device on stage because you will really experience it when you wear it. It's very difficult to convey, actually, how it feels to wear it. But I have a little video. Hopefully, I can play. It's off YouTube. It takes a minute of how this would. What is it that this device do right now? Let's see if it plays. And has sound. I don't know if the sound is going to play. You have the sound?
Okay, Glass. Record a video.
This is it. We're on in 2 minutes.
Okay, Glass. Hang out with the Flying Club.
Google photos of tiger heads.
You ready? You ready?
Right there. Okay, Glass, take a picture.
That is awesome.
Okay, Glass, record a video.
After this bridge, first exit.
Stay delicious and Thai. Arrowhead.
Google jellyfish.
Well, let's see. It's beautiful.
So you saw some of the capabilities of the device. Really, actually, as we released this to a number of people and they tested it, it was really amazing to experience life through their eyes, because they managed to capture some shots that prior to this date, they've never been captured before. And you also saw some of the other capabilities of the device in terms of asking questions, doing live translation for you, doing video conferences, taking pictures and sharing very quickly. There's one point I also wanted to make about the hands-free aspects of this. We noticed actually very early on that if you want to have an electronic device that you wear the whole day, and this one actually lives on my head, this really should not impede any of your regular senses. So you notice that my eyes are totally open, so I can maintain eye contact with you if I wanted to, even though I can see information because the display is to the side. You notice that my ears are open, so I can totally hear what's going on in the environment, even though I have an audio system that can get sound back to me. And you notice that my hands are totally free when I use this device. So that was really important. Eyes free, ears free, hands free. So you can live your life normally the way you would live your life, but have very, very rapid access to technology when you need it. And when you don't need it, it's totally out of the way, so you can just forget about it and go about your business. Now, I think this is actually pretty cool. So we've taken a very interesting, solid first step towards what we wanted to achieve. Let me just take a couple of minutes and tell you why this is available and doable right now. And first and foremost, this is possible right now because of you guys, because of what you enabled in the electronics industry, especially with the smartphones in the past 10 years being a major driver of innovation, of miniaturization, and lowering the power of entire systems. That has been a huge boon to us, and we've absolutely taken advantage of that infrastructure. It would have been extremely difficult for us to build our systems if the smartphone revolution had not happened prior to this. And obviously, the SoCs in these cell phones are very, very impressive. I'm an electrical engineer by training, or partially, and I'd really love actually see how sophisticated these systems are. But it's also important to note that these are not pure electronics. There's a lot of other things in a typical smartphone, and we've taken advantage of those also. Just to give you an example, the cameras in the smartphones have come a really long way in the past decade or so. So early 2000, these were a few 100K pixel, very poor image quality. And over the years, actually, the smartphones, typical commercial smartphones, state-of-the-art smartphones, have gone to the point that essentially the picture they take is acceptable for most typical uses of a consumer. So for many scenarios, you don't take your camera with you anymore anywhere. The cell phone is great. And these are very sophisticated objects. So if I think of a typical state-of-the-art cell phone camera module, this is many megapixels, has multiple lenses in it that have micron-level precision in making, or sub-micron sometimes, making the lens. Definitely micron-level precision of assembling the system. It has electromechanics, so it's mechanical, electrical, actuators, sensors, light engineering, all that stuff put together. It produces a beautiful image, and it costs a few dollars, which is mind-boggling, actually. This is possible today. But we've taken advantage of these technologies to build Google Glass, and hopefully in the next period of time also, as the various platforms coexist together, we can take advantage of those. But this is also one of the reasons that this device was not doable maybe 15 years ago, because there was no sophisticated gyroscope, which is very important for us. Cameras, a lot of progress in SoC, the SoCs that you guys have enabled. None of the stuff was available 15 years ago. Now we can do it. So thank you. The second big change is now the existence of data networks. So we realized actually that these devices are powerful only if they're connected, if they have data connectivity. And 20 years ago, this wasn't really even 15 years ago, this wasn't really possible. There was no high-speed mobile data network widely available. So with the inclusion of data, this really fundamentally changes what you can do with this device. So this is not purely just a camera or even a TV screen. This is genuinely an interactive, intelligent device which is connected, which is taking me to the last part of why this is possible right now, and that's the cloud and it's essentially the data center infrastructure, which again, for the most part commercially and in a wide consumer base for regular people, it didn't really exist. But I would like to invite you to think about using glass or even your smartphones as using a supercomputer for a fraction of a second. This is what's really going on here. So when you use a Google service, you have a gateway device of sort that you interact with. You send a query to Google. You request something that may relate to maps or search for information or analytics. And that puts Google to work. But that's sometimes many millions of cores actually working for you for a very, very tiny fraction of time, and then getting the response back to you. So this really, the combination of data connectivity and these massive data centers that the number of companies are running right now, they have put supercomputers at the fingertip of consumers, which is again transformative. So we'll see actually how that's gonna impact what's gonna happen in the next period of time. Now, I apologize that it took longer than what I intended. Now, to wrap this up, I just wanted to say also a couple of words about where this is going to go and what's going to be important for it. I think the best technology is what's going to eventually disappear, so you don't even know the technology is there. That's one of the reasons I really like Kinect. I think Kinect is incredibly creative. It's a great user interface with the computing system because you carry nothing. You're yourself, and you move around, and you interact with the computing system. This is how it should be. This is fantastic. For these types of platforms, these types of form factors, also, we should push for making this as the least possible intrusive, and eventually push for making the technology disappear back into the background. So that's where we want to go. And one of the main drivers for this is going to be obviously optics and photonics because of the display that we have. We absolutely need further miniaturization in every single part of the system that you can think of, and I discussed in the past few minutes. Very important for this is going to be transducers. Right now, we have a number of transducers in this device that we use for interactions with the environment or the user, gyroscopes, accelerometers, even the camera, other sensors that we have here. More transduction mechanisms, miniaturized low power, will be important for this platform, for having this platform interact with the body. There's lots of different ways that you can imagine this platform can interact with the human body, and also it has to interact with the environment. This is a device, an electronic device that's out and about. It doesn't live in my pocket. It sees the world. It can potentially smell the world. It can do other things. So we have to think about what other transducers can actually live in this device, and the device eventually will live with us throughout our lives. We definitely need more computing power in these devices. What we have today is a good, solid first step, but not enough, especially for video processing. Because more and more so, if this platform is successful, we're going to capture a lot of video. We'll be continuously, maybe sometimes capturing video if the user allows it for maybe an hour or for whatever period of time. We'll be analyzing this video, and then according to what the user wants, we may be, if augmented reality, for example, is the application, we'll be superimposing some computer-generated graphics on top of that video. This takes a lot of actually processing power. Stabilizing it is very difficult, so we need a lot of computing power. We need to handle a lot of video. We need to handle a lot of computer graphics, and definitely that need is there. And obviously, everything has to be ultra low power for this form factor, because there's some very hard limits of what you can do here. You cannot make it very heavy because it will not be comfortable. But assuming that we managed somehow to pack a big processor there and some battery that had massive capacity, still you cannot burn a lot of power here because you have to dissipate the heat. And this is very close to my body, so it's going to be uncomfortable. So it has to be cool and comfortable and stylish, which all of those actually put a lot of constraints over how heavy this can be, how big the components can be, it's very, very challenging. So we need very low power designs, especially in SoC or eventually any other component that goes into the system. Now with that, I would like to conclude my presentation, say that we're very excited about this platform. Potentially, this could be a major next platform in computing and communication. As before, it will coexist with other platforms. So you notice that still we have a lot of data centers and big computers. We have a lot of PCs. We have a lot of tablets and notebooks. We have a lot of smartphones. So as the new platforms have appeared, the previous platforms have not totally disappeared. They're completely valid, and there's market for it. They will coexist to some degree, but the leading edge actually may change. I think we're excited about this. I think we've made some really solid progress in the right direction, and hopefully we can accelerate that progress. Thank you very much.
Okay, and with that, let's open up for questions.
David Cantor. So, it's actually pretty exciting to see all the new capabilities here. And one of the questions I'd have for you is, how do you see sort of the security model for computing change as a function of this? Because going back to what Bob Caldwell said earlier, the whole notion of apps and national security, you really don't want to have to reboot your nuclear weapons. Right, and in the same way, there's a lot of very different security implications here.
Yeah, we definitely take the data security very seriously. The current model of the system doesn't have apps per se, so there's capabilities that we can enable. And in the current form, there is no program that you would run on this directly. So everything is actually pushed from the cloud. Even though in the next period of time, we'll probably change that and allow people to run things more natively here. But yeah, that's definitely very important.
So are there any things in particular that you think are fundamentally different about security for this platform than, say, a conventional computer or smartphone?
I think this has a lot of common issues with the typical smartphone. Maybe go to this side first.
Yeah, Babak, Jack Dong from Oracle. So you said in your slides that this Google Glass can send audio and capture image immediately and send to your friends through long distance. And it can do voice command to do search. So I guess a lot of us, I know here, a lot of us are thinking of this question. Fundamentally, what does Google Glass that can do that an iPhone cannot?
So I think a lot of it, that's an interesting question, but a lot of it goes back to the uniqueness of the form factor I mentioned to you. Number one was immediate access to computing. So instead of me trying to fidget with my phone, take it out, unlock it, it's very immediate. Number two is potentially information overlay, which a smartphone would not be able to do because it's unlikely that people will walk around and for any extended period of time they would hold their cell phone out to look at stuff. Number three is the potential for very large screens. So the cell phone screens, no matter what, are going to be limited for the most part to what the cell phone itself is. So it would be very difficult to get a cinema-sized display in front of someone if you don't have a form factor like this. Number four would be the hands-free aspect of this. So I wear this basically day in, day out. It's always with me. I don't need to worry about it. And I can do whatever I want to do. I live my life basically not worrying about a piece of electronics that I have to fidget with my hands. But again, a smartphone would not be able to do this. Having said that, we are a huge proponent of smartphones. We ship lots of them actually with Android, hundreds of millions of them. So that's a very important platform for us. So this is not to say that the smartphones are not good, but there are certain things that are definitely unique to this platform that a smartphone would not be able to do.
Okay. Just a quick follow-up. So for those of us already wearing glasses, I'm trying to get rid of it. So how are you going to convince me to get another pair?
Well, first of all, actually, at the moment, the kind of device I'm wearing actually is not suitable to be worn over your glasses. So in the next few months, we'll release a version that would integrate into glasses. So if you're wearing your glasses, you'd be able to use this. And my prediction is this is difficult, but if the platform is successful, you will see different types of optics here. They would look different.
Okay, thank you.
Yeah.
John Massey, I have a question that actually oddly relates to a past Hot Chips. In 2007, I got the computer scientist, science fiction author Werner Vinge to speak here. You probably know this guy. He had just won a Hugo Award for Rainbow's End, in which basically everyone had contact lenses that were the moral, descendant of these. And so here's the question for you. The problem raised there is that there was sort of the logical equivalent of Wikipedia edit wars as people tried to impose their own ideas on the reality that was shared amongst everybody. This sort of gets back to the security. Do you guys worry about if somebody asks a question, do they actually get the right answer, or what is the right answer?
So it's actually interesting. Thanks for the question. It's very interesting that you mentioned contact lenses, because I used to be a professor at the University of Washington, and we actually used to work on putting displays on contact lenses, and we published a bunch of papers. So it was fun. We went all the way to 1 pixel on a contact lens that worked wirelessly, but even that was quite difficult. In principle, that's a doable thing. Someday, actually, in the future, those contact lenses may arrive. It's not immediate, it's not near future. But I think stepping back and thinking about the nature of interaction of the person with this type of device, whether it's in the form of a contact lens in the distant future or this form today, I think one of the major things that we looked at was to always put the user in charge. So they're always in control. So we don't want the computing system to be in control. We want the person, the human, to be in control. So you set basically how you're going to interact with this device, how this device is going to interact with you, if it's allowed to interrupt your life, it's not allowed to interrupt your life, and also what data sources it's going to use basically to give you information. So I think we really should put the human in charge, and I think that would be a better way of going forward. Yeah.
Yes, Jack Schrickett, NVIDIA. You seem to emphasize the fact that it's integrated and that the whole package is integrated right close to your eye. Why wouldn't you consider, or why do you think about having the compute in your pocket, only the display and the camera near your eye?
It's a good question, actually. And a long time ago, we had devices like that. So either with the wire going to a controlled box. Some of it is actually for historic reasons of why this actually ended up. Historic meaning how the group evolved and what the state of the technology was at that particular point in time and the state of software. But I would say actually there's 2 things to think about here. This is a very valid point. One is how much computing power you can have here versus here, and the other thing is latency. We actually experimented with sometimes actually having the processor somewhere else, and for some of the applications, the latency was a bit too long, unfortunately. And this is very, very sensitive to latency. You really need to, in order to have a seamless interaction with this system, it has to be very responsive. So that didn't work that great. But it doesn't mean that in the future that's not necessarily a viable way to go. It's actually possible. Yeah.
Hi, my name is Aditya. I work at Intel. So why is the design unsymmetrical? Why don't you have something similar on the other side with a second camera and even more sensors?
That's a good question. There's a lot of complexity in having a binocular system, which relates to the optics design complexity and the human vision physiology. So it's not really doable to simply replicate what we have on this side and put it on the other side. But also, if you do that, you immediately double a lot of system parameters such as weight and power consumption that we've been trying hard to minimize. So really the balance was between having a very powerful system, but at the same time, having a system that's comfortable and is possible to wear over very extended periods of time, because we wanted people to wear this basically the whole day. So the comfort was very important, and this was really the first design that we had that was comfortable enough that people could wear it the whole day. Yeah.
Yes, Satoshi Matsushita, NEC. As you mentioned, the deeper, the effective, the information sharing between people wearing the glasses, the cloud and the device interaction is very important. But I think that the architecture or the paradigm is still the same. Is there any move for the future programming paradigm that enables better interaction between the cloud and devices and so on?
So in terms of architecture, do you mean the SoC architecture or the
software systems or the SDK or some or all of those things?
I think as these platforms progress, there's similarities always between the previous platforms, but if I hazard a guess and sort of look at the trajectory of how this may evolve in the next few years, to me it looks quite different actually from what we've had in the past. So we definitely work on not just the system level software here, but the overall architecture of how this whole system is going to work, and it looks quite different. So we'll see how it's going to evolve.
Okay, thank you.
Yeah.
Hi, Kevin Krimmel from the Lindley Group. Actually, a couple of two-part questions. The SoC you're using today is probably an off-the-shelf product processor. It looks very similar to the one in the Galaxy Nexus processor. Do you see that evolving into a custom SoC for this project? Also, the only thing missing from making glass a full cell phone is the cellular radio. You have almost all the sensors. You have the Wi-Fi, Bluetooth. Do you also see that evolving once you get past the Explorer Edition to a full cellular radio in addition?
So we have taken advantage quite a bit of the ecosystem that smartphones have created, especially for SoCs. It's been wonderful for us. Going forward, I would say if we see an alignment between the trajectory of where glass and wearables go and where the cell phones go, then we can take advantage of those components and infrastructure. If there's a divergence, then we have to do custom things. In terms of the cellular phone modem, there is no plan of putting a cell phone modem immediately in glass, like right now.
Thank you.
Yeah.
Hey, you want to go ahead? Okay. I have a power question. So, do you have some ballpark number about the power of different components inside the Google Glass? Because as we know, in cell phone, the 3G modem and the display is the major contribution of the power. But Google Glass got rid of both of them. For the rest of the system, which parts consumes more power?
Yeah, we're very power sensitive, and one difference that we have between this device and cell phones is our battery is smaller, because we can't have a very big, heavy battery in this device. It's true that we don't have a cellular phone modem in this, but we need very frequent actually connectivity between this device and other places, whether through Wi-Fi or Bluetooth. That happens quite often. We need also minimum latency, so some of the things that people may turn off in cell phones, we may not be able to turn off. So there's a lot of trade-offs there. In terms of the display, the one big advantage that we have is that a lot of the photons that we generate directly go into your eye instead of illuminating the environment, so we can, in principle, make the display much more efficient than any other device that just basically produces an image for everyone.
So do I understand correctly that the communication dominates the whole power budget compared to computation and display? Is that the case? No. So which part?
I didn't say actually which part dominates, but just discuss some of the trade-offs.
Okay. Thank you.
Yeah.
Bob Massley at Oracle. As we're successful with these devices and make them imperceptible, maybe we swallow them and they self-embed in our stomachs. How do we deal with them becoming invasive? You pointed out that we will always leave the human in control of them, but which human? Suppose I'm having a conversation that I do not want to have bugged or recorded. How do I know my other's presence are turned off?
That's a good question. So first and foremost, we'd like to put the user in charge. That's the most important one. The user of the device, the person who is using the device. But the second point that you're raising, it's already actually an issue because this phone may be recording right now. And you have no way of knowing that. There's an element of basically of societal trust that we have to build, and there's an etiquette of using these devices that we have to figure out. But those issues are not for this one only, is not for future only. Those issues are present right now, today. You need to have a conversation in the broader society of how we're going to deal with that. Good point. Yeah.
Hi, my name is Diego, LSI Corp. I would like to understand what kind of applications in terms of video technology the Google Cloud is going to offer, like video analytics, image stabilization, compression, stereo capture. You could do it, so I would like to understand that.
So we do actually a lot of it already. So we definitely do compression, we do stabilization. There is a roadmap for that. So I think at an opportune moment in the future, we'll share that. And last one, I think. Yeah.
Hi, this is Sarah Biabani from Intel and also IEEE Standards Association. So I've been working on some standards for the smart grid, and some of them had to do with this smart meter. And the smart meter, the electric company can gather a lot of information about you, your patterns of behavior, and so forth. And so we had to be very concerned, the standards, to kind of have this notion of privacy, which you've heard, and I think it's quite talked about in Europe, perhaps more than here. So you're enabling everyone to capture an image of everyone else around without their consent. So are you prepared to build some kind of a provide some kind of a mechanism that allows people to opt out of your pictures?
That's a really interesting point. And it reminds me of actually an article in New York Times from late 1800s when the first cameras came out. And there was a huge uproar about it because now you can walk down the street and someone actually may come up to you and take your picture. And that was unprecedented. That's 1880s, 1890s. And it really actually made a lot of people uncomfortable. So it took some time, I think, for the society to sort this out, that there is going to be a device, a camera. This device can catch your picture. If you're in a public area, actually, someone may snap your picture. It's legal in the US and pretty much all over the world. And the user of the camera is going to exercise good judgment. Obviously, you have paparazzis and those kind of things that are very invasive of people's privacies. But it took some time, actually, for the society to figure out actually what this is going to be. I think the trajectory for a device like this is going to be something similar. In principle, it's nothing new that you can take pictures and videos of people because right now this is happening. So people's voices are getting recorded, and there's a lot of pictures being taken either from people's personal devices or cameras that are installed all over the place. But I think it's a valid point. We have to have a conversation of what it means to be in the public place. What is it that we expect actually as something private, and what is it that we expect that be recorded and shared by others? It's a valid point.
Okay, Babak, thank you very much for a very interesting presentation, and thanks to the audience for a very interesting set of questions.